Hello everyone, this is Dr. G. Karthik Reddy working as Associate Professor in the Department of EC, MLR Institute of Technology, Hyderabad. Today's session topic is stationery process. In that we are discussing about wide sense stationery and strict sense stationery process. In this lecture we are going to discuss about wide sense stationery, strict sense stationery and examples of wide sense stationery process. Wide sense stationery process. The wide sense stationery process is also known as weak sense stationery process. Why it is called as weak sense stationery process means here we are considering only up to the second order stationery process. We are not discussing up to the nth order stationery process. Generally we are taking this, we can consider this as approximation to the original random process. Okay, whatever the random process we are having, we are taking the up to the second order stationery process only. That it means we are taking the approximation to the original random process signal. That is why we are calling this as weak sense stationery process. However, here next, the condition of weak sense stationery process. The condition of weak sense stationery process, that is mean must be constant. Mean or expectation of random process. First condition is, expectation of random process must be constant. Expectation of random process must be constant means the first order stationery must be satisfied. Now next second condition. Second condition is autocorrelation function. Expectation of x of t into x of t plus tau is equal to what? Rxx of tau. Rxx of tau is equal to expectation of x of t into x of t plus tau. Autocorrelation is applicable only for the same signal with its delayed version. Means here the condition of wide sense stationery process means autocorrelation must be independent of time t and dependent on the time difference, that is tau. Now next, this is related to the wide sense stationery process. Wide sense stationery process. And next here, now when if you are considering jointly wide sense stationery process, jointly wide sense stationery, you are going to get one more concept is a jointly wide sense stationery process. Jointly wide sense you are occurring only when you are having two different random process, x of t and y of t are two different random process. Then the condition of jointly wide sense stationery, it tells that the expectation of random process x of t must be constant. Must be constant. Expectation of y of t must be constant and cross correlation function must be function of time difference. Cross correlation function must be function of time difference. Just now we discussed tau is equal to t2 minus t1 means difference of time instants of t2 minus t1. This is the definition of cross correlation function. This is the definition of cross correlation function. Just now I discussed that the mean of expectation of x of t must be constant. Expectation of y of t must be constant and expectation of x of t into y of t plus tau must be equal to independent of time t. Independent of time t. We can conclude that for wide sense stationery process, mean or expectation of random process x of t must be constant and autocorrelation function is independent of time t. These two conditions must be satisfied if the random process is said to be, random process of x of t is said to be wide sense stationery process. Now next, if they are calling that as jointly wide sense stationery process, then expectation of x of t must be constant, expectation of y of t must be constant and cross correlation function must be independent of time t. These conditions must be satisfied if the random process x of t and y of t are said to be jointly wide sense stationery. Now next, we are going to discuss about S process. S process is called strict sense stationery. Strict sense stationery process. Strict sense stationery process and a random process x of t is said to be strict sense stationery if its nth order joint density function does not change with time or shift in time value. Okay, if you are considering for up to x1 to xn, okay, if you are considering for example, okay, for example, a noise is occurred in a particular wireless channel. Okay, this is a one of the different time instance I am taking. Okay, this is the time instant t1, this is the time instant t2, this is the time instant t3, and this is the time instant tn. Okay, each time instant you are having x1, x2, x3, so on. Okay, if you are considering the density function we are calculating for each and every instant. Okay, now when you shift the time shift, okay, the small change in time must not be varied. Okay, it must be same. It must be same. Then it is called as SSS process. Okay, strict sense stationary process, or we can also call this as strong sense stationary process. Also, we can call strong sense stationary process. Okay, if the density function fx of x1 comma x2 so on up to xn semicolon t1 comma t2 so on up to tn must be equal to fx of x1 comma x2 so on up to xn, t1 plus change in t, t2 plus change in t, so on up to tn change in t. Okay, if you change the time instant, okay, then the function must not be changed. Okay, but both the conditions are satisfied. Okay, these two condition is satisfied, then we are calling this as strict sense stationary process. This is applicable for up to nth order movements. Okay, okay, if you are considering up to 2, okay, up to 2, if you are considering up to second order, that is called weak sense. Means SSS process can also be become weak sense, but weak sense cannot be become as SSS process. Converse is not true. That only we are discussing here. Okay, SSS process is also known as wide sense stationary process, but wide sense stationary process cannot become as SSS process in all the sense. Okay, this is a weak sense. It is called strong sense stationary process. Okay, in this session we have discussed, okay, what is that WSS process and SSS process. We will discuss with an example. Okay, here a random process x of t is equal to at. A is uniformly distributed random variable for the interval 0, 2. Find whether x of t is wide sense stationary or not. Okay, here A is uniformly distributed random variable. Okay, we already discussed in previous sessions that if x is a uniform random variable, okay, x is a uniform random variable, and fx of x, uniform random variable, is defined in between the intervals. Okay, here x in between a to b, if it is constant, then fx of x becomes, what is that, fx of x is equal to 1 by b minus a for the interval a less than or equal to x less than or equal to b, 0 otherwise. Okay, here the random variable here they are telling as a, then fa of a is equal to 1 by b minus a. Here what is that, 0, 2, they given the values, then 1 by 2 for the interval 0 less than or equal to a less than or equal to 2. Okay, this is the condition. First we have to solve this one. Fa of a is equal to 1 by 2. Now next we want to calculate whether the x of t is wide sense stationary or not. For that, first we have to calculate expectation of x of t. We have to show that expectation of x of t is constant. Next, autocorrelation function must be what, function of time delay or independent of time t. If these two conditions are satisfied, then the given random process is a wide sense stationary process. Now we are going to discuss the problem related to this. Okay, expectation of x of t. Okay, solve the problem. Solution of this. Expectation of x of t, integral minus infinity x of t into fx of x comma t. Okay, x comma t dx. Here x of t, it is given at, integral minus infinity to infinity. Okay, here instead of, okay, at, here fx of x of t dx. Here it is defined for the uniform distributed random variable for the interval 0 to 2. Okay, 0 to 2, a you can take outside, t into 1 by 2 dx. Now you simplify it further, then what you are going to get, a into t square by 2, t square by 2. Okay, here a by 2 Okay, then what you can simplify it further, a by 4 t square 0 to 2, then a by 4 4, then a means which is constant, means we got expectation of random process is constant. Now second condition is what, autocorrelation must be independent of time t. Then what you are going to get, expectation of, what is the formula, x of t plus tau. Then you substitute this one, integral minus infinity to infinity x of t, at into a into t plus tau. Okay, here uniformly distributed random variable, again here 1 by 2 we are going to get. Then what you are going to get, here you change the limits. Okay, here change the limits to 0 to 2. Then what you are going to get, you simplify it further. Okay, a square by 2 0 to 2 t into t plus 2 of tau. Okay, now what you are going to get here, a square by 2. Okay, here what you are going to get, tau is a, okay, take it common, 0 to 2 t square plus t tau dt. Then you simplify it further, what you are going to get, a square by 2 t power 3 by 3. Okay, 0 to 2. Okay, now plus here t, tau is outside, tau you take outside. Then here what you are going to get, t square by 2 0 to 2 tau. You simplify it, you will get in terms of tau. Means here what you are going to get here, autocorrelation function you are going to get in terms of tau. Okay, you are going to get a square by 2, a square by 6, here 8 plus here what you are going to get, a square by 2 4, means a square by 4, here what you are going to get, 4 into tau. Okay, you are getting in terms of tau, means here it is satisfying, autocorrelation is function of tau, then both the conditions are satisfying, then given random process is wide sense stationary process. In this session we have discussed, okay, first in this we have discussed about the wide sense stationary process, triple process. Next we have discussed the problem related to wide sense stationary problem. One problem we have discussed related to wide sense stationary problem. Okay, thank you.